Welcome back. Let's practice finding tangent planes and normal lines. All right, so here's our first example. We want to find an equation of the tangent plane and find a set of symmetric equations for the normal line to the surface at the given point. And we're given z is equal to x squared plus y squared plus 3 and the point 2, 1, 8. Okay, so to find the equation of the tangent plane and to find a set of symmetric equations for the normal line, we need two things. We need a point, which we've been given, and we need a normal vector. And that's what we need to find. And to find that normal vector, we need to get our surface equation in the following form. We need to have a function of three independent variables, x, y, z, equal to some constant value c. Okay, so our original surface equation here, we would think of as a multivariable function f of x, y, where z is the dependent variable. But when we want to find a normal vector at a point on a surface, you have to change the way you look at that function. What we want to do is get all of the x, y, and z terms on one side of the equation such that they are then just equal to a constant. And in that form, we can view the surface as a level surface of a four-dimensional shape represented by a multivariable function of three independent variables. Okay, and the reason for that is because then we can find the gradient vector for this function, which will be a three-dimensional vector that is the normal vector at a point on a level surface, or in our case, the surface we've been given. Okay, so that's the general idea of what we're going to do. If you want more details on the why, feel free to watch my lesson video for this topic if you haven't already. But that's as far as I'm going to dive into the details of why in this video. I just want to focus on the math and solving these example problems. So our goal here is to first get this equation in this form. We need to get all of the x, y, and z terms on one side of the equation such that they are then equal to a constant. Okay, so to do that here, we can subtract x squared and y squared from both sides, giving us z minus x squared minus y squared equals 3. Right, now we have all the x, y, and z terms equal to a constant. So we are in this form of the equation of a level surface, which means that we can now find the gradient vector of this function. And so that will look like this. The gradient of f of x, y, z is equal to the partial derivative with respect to x times I plus the partial derivative with respect to y times j plus the partial derivative with respect to z times k. All right, so starting with the partial derivative with respect to x, and remember we're looking at this form of the function, specifically just this side of it, you can ignore the constant, and the only term that is in terms of x is negative x squared, and the derivative of that will be negative 2x, so this will be equal to negative 2x times I, and that's it because negative y squared and z don't have any x's in them, so they are constant terms whose derivatives are 0 with respect to x. All right, but then for fy, z and negative x squared are constant terms, their derivatives are 0, but then negative y squared, the derivative of that would be negative 2y. So we have minus 2y times j plus fz, or the partial with respect to z, and negative x squared and negative y squared, they would be constants with respect to z, so their derivatives are 0, and then the derivative of z is 1. So we have plus 1k, or just k. All right, so that right there is the gradient vector for this function, and it represents the normal vector for every level surface at any point on this function. Okay, but now what we want to do is find the specific normal vector to a specific level surface. And we can do that by plugging in the coordinates of this point into that gradient vector. That will give us the specific normal vector at that point on this surface. Okay, so we're going to take our gradient vector and evaluate it at the point 2, 1, 8, and that will be equal to negative 2x, so negative 2 times 2, which is negative 4, so negative 4i, minus 2 times y, or 2 times 1, which is 2, times j, plus k. There's no variables in that term, so there's nothing to evaluate. All right, but this right here is the normal vector that we need to find an equation of the tangent plane and a set of symmetric equations for the normal line to this surface at this point. Right, to do that, we just have to remember the form of an equation of a plane and the symmetric equations for a line in 3D space. And so remember from earlier in Calculus 3 that the setup for the equation of a plane is this equation right here, where a, b, and c are the components, specifically the x, y, and z components of the normal vector, and x1, y1, z1 are the coordinates of a point in that plane. And then for the normal line, remember that a set of symmetric equations for a line in 3D space looks like this, where once again, a, b, and c are the components of a vector that has a direction that you want for that line. So in this case, if we use the components of a normal vector, we will get a normal line, and then x1, y1, z1 are the coordinates of a point on that line, which will be the same point that we're going to use for the tangent plane, which is this point right here that we've been given, right? That is the point where we want to find the tangent plane and normal line on this surface. Okay, so let's set it up. In this case, the x component of the normal vector is -4, the y component is -2, and the z component would just be 1 since we just have k. And then don't forget the x, y, and z coordinates of the point are 2, 1, and 8. So altogether, we get this. We have -4 times x minus 2 plus -2 times y minus 1 plus 1 times z minus 8. And that's equal to 0. And so then simplifying, you just want to distribute each of these values through their respective quantities. So we have -4x plus 8 minus 2y plus 2 plus z minus 8. And that's still equal to 0. All right, and then you do want to make this look nicer. So do some simplifying. And notice that we have a +8 and a -8. Those will cancel out. So I'm just going to cross those out. They add up to be 0. And then that just leaves us with -4x minus 2y plus z equals -2, right? To make it look nice, you would want to move the constant to the other side of the equation. That way you just have the x, y, and z terms on one side, and that would be the equation of the tangent plane. But usually it's not common to have the constant be negative, so if you want, you can negate both sides of the equation, and it would still represent the same plane. I'm going to do that here. I want this to be a +2 to make the equation look nicer, so I will change the sign of the three terms on the other side as well. We'll have +4x, +2y, and then -z. Okay, you can just think of it as swapping sides of the equation, but this right here would be the equation of the tangent plane at this point on this surface. Then for the normal line, it's a little bit easier of a setup. There's less simplifying to do. We'll have x minus the x coordinate from the point, which is 2, divided by a, which is -4, and that will be equal to y minus the y coordinate, which is 1, divided by b, which is -2, and then that will be equal to z minus the z coordinate, so z minus 8 divided by c, which is 1. And you could leave it like that, but another way to do it is to write it as just z minus 8, since anything divided by itself is 1. Okay, and that right there would be a set of symmetric equations for the normal line to this surface at this point. Okay, and once again, as with the tangent plane equation, these are not the only correct answers, which is why the problem says to find an equation and find a set of symmetric equations, not the equation or not the set of symmetric equations. Because there are multiple different equations that could represent the same plane, or multiple different sets of symmetric equations that would represent the same line, which is something that we talked about earlier in Calculus 3 when we first learned about the equation of a plane and the symmetric equations or the parametric equations of a line in 3D space. Okay, your answers can differ by some common factor, that is okay, but these are going to be my final answers for the equation of the tangent plane and the symmetric equations for the normal line. Okay, let's take a look at another example. For our next example, we once again want to find an equation of the tangent plane and find a set of symmetric equations for the normal line to the surface at the given point. And we've been given the surface z is equal to y times e to the power of 2x times y and the point 0, 2, 2. All right, so once again, what we need to find here is a normal vector at this point on this surface that we can use to create an equation of the tangent plane and a set of symmetric equations for the normal line. And so what we need to do first is get our surface equation in the proper form. We want all the variable terms on one side of the equation. All right, in this case, what I'm going to do is subtract z from both sides. So we'll have 0 is equal to y times e to the power of 2x times y minus z. All right, and so now we have it in the form of a multivariable function of 3 independent variables equal to some constant, in this case 0. So now it's in a form where we can find the gradient vector, okay? So our function f of x, yz is equal to y times e to the power of 2xy minus z, and now we want to find the gradient for that function, okay? And that will be equal to fx times I plus fy times j plus fz times k. All right, so let's start with the partial derivative with respect to x. Looking at this function here, we can ignore negative z. That's not in terms of x. It's a constant whose derivative would be 0. But then for this term, x is in the power of this exponential function, so we do need to take the derivative of that. Okay, we'll keep that y in front of it, but then the derivative of an exponential function is just that exponential function, but then multiplied by the derivative of the exponent. Okay, so what we'll get here is y times e to the power of 2xy multiplied by the derivative of the exponent, which with respect to x would be 2y, because x is to the first power, so its derivative would be its coefficient, or the constants multiplied by it, which is 2y. Okay, so we multiply by 2y, and that gives us the x component for the gradient. Then we will add that to the partial derivative with respect to y, and that's going to be a little bit trickier, because we have y times an exponential function that includes y in the exponent. So what we have here is a product of two functions in terms of y, so we have to use the product rule for derivatives. So let's work on that here. We'll take the first function of y and multiply it by the derivative of the second, but with respect to y. So we'll just rewrite that exponential function, but then multiply it by the derivative of that exponent, which with respect to y will be 2x because y is to the first power, so its derivative would be its coefficient. So we multiply by 2x, and then we add that to the second term for the product rule, which will be the second part times the derivative of the first. And so you'll have e to the power of 2xy times the derivative of y, which is 1. Okay, so you just get e to the power of 2xy, and that's it. All those terms together make up the y component, so multiply them by j. And then finally, for the z component, we need to take the partial derivative with respect to z, and that term that we've been working with so far, we don't have to worry about because it would just be a constant with respect to z. There's no z's in it, so its derivative would be 0. Just focus on this term, the derivative of negative z, so we get minus k. All right, and then before we evaluate this gradient vector at this point to get our normal vector, I do want to simplify this just a little bit. You can multiply these y's and get y squared. So this would be equal to 2y squared times e to the power of 2xy times I plus this term, which I'm just going to rearrange a little bit. We'll have 2x times y times e to the power of 2xy plus e to the power of 2xy times j minus k. All right, and now I'm going to plug in the coordinates of this point into the gradient vector to get the specific normal vector at this point on this surface. All right, so the normal vector will be equal to del f of 0, 2, 2, or in other words, the gradient evaluated at 0, 2, 2. So we'll plug in 0 for x, 2 for y, and 2 for z, which there are no z's. So really you just have to worry about plugging in 0 for x and 2 for y. So this will be equal to 2 times y squared, which is 2 squared, times e to the power of 2 times 0 times 2, and that's multiplied by I, plus 2 times 0 times 2 times e to the power of 2 times 0 times 2, plus e to the power of 2 times 0 times 2 times j minus k. Okay, now simplifying, all of these powers of e are just going to be 0 because you have 2 times 0 times 2, 2 times 0 times 2, 2 times 0 times 2. That's just going to be 0 every single time, which means you have e to the power of 0, which is just 1. So each of these e's just become 1, and then this term is going to be completely gone because we're multiplying all these pieces by 0. So I'm just going to cross that out right now. That goes to 0, and then we can make a pretty nice simplification here. We will get that the gradient is equal to 2 times 2 squared, so 2 times 4, which is 8, times e to the power of 0, which is 1. So we just have 8i plus e to the power of 0, which is 1, times j, so we just get j, and then the last term is still minus k. Nothing changes there because there was nothing to plug in for that term. Okay, and so this is the normal vector at this point on the surface, which means now we can use it to find an equation of the tangent plane and a set of symmetric equations for the normal line at that point on this surface. So let's do that. And starting with the tangent plane, once again, this is the setup for the equation of a plane. In this case, A, B, and C are 8, 1, and negative 1. Those are the x, y, and z components of the normal vector, which is our gradient vector, evaluated at this point. And then those coordinates x1, y1, z1 are these coordinates of the point, 0, 2, 2. So here's what we get. We'll have 8 times x minus 0 plus 1 times y minus 2 plus, or really minus, because c is negative 1, so we have minus z minus 2, and that's equal to 0. So simplifying, we get 8x plus y minus 2 minus z plus 2 equals 0. And then notice that we have a positive 2 and a negative 2, so those cancel out, which means we have no constants left over. So one way that you could represent this tangent plane is with this equation, 8x plus y minus z equals 0. But since the coefficient of z is just negative 1, some people may prefer to move that over to the other side of the equation, and you'd have z equals 8x plus y, which looks a little bit cleaner. Either way, both answers are correct. Both of them would be equations of the tangent plane that we are interested in here. I'll just write or so that you know that they are the same plane. Okay? But then for the normal line, you'll have x minus x1, which is 0, or really just x. So I'm just going to write x divided by 8, which is a, and that will be equal to y minus 2 divided by b, which is 1. So you could leave it like that, or you could just write it as y minus 2, because anything divided by 1 is itself, and that will be equal to z minus 2 divided by c, which is negative 1. And that right there would be the set of symmetric equations for the normal line to this surface at this point. Next up, we want to find an equation of the tangent plane and find a set of symmetric equations for the normal line to the surface at the given point. And we have y times the natural log of x times z squared equals 2 and the point e to 1. Okay, so this is just like the previous two examples. We're going to go through the exact same process, just for a different function and a different point. And the first step has already been taken care of for us, right? Our surface equation is already in the right form. We have all the variables on one side of the equation equal to some constant. All right, so our multivariable function f of x, y, z is equal to y times the natural log of x times z squared. And so we can move right into finding the gradient vector here. So we'll take the gradient of f of x, y, z, which again is equal to fx times I plus fy times j plus fz times k. And so starting with the partial with respect to x is inside the natural log function here. So we do need to take the derivative of that function. Remember that y is just a constant here. It's a constant multiple. So it will tag along. Don't get rid of that. We will get y times the derivative of this natural log function. And remember that the derivative of a natural log is 1 divided by the inside function times the derivative of that inside function. So we have 1 divided by x times z squared times the derivative of x times z squared with respect to x. So that would just be z squared. Because x is to the first power, its derivative would be 1. 1 times z squared is z squared. So we're multiplying by z squared, and that gives us the x component. All right, then for fy, we need to take a partial with respect to y, and the only y in this function is right here. It's not inside the natural log function, so with respect to y, this is just a constant, and we just need to take the derivative of y to the first power, which would be equal to its coefficient, which is 1 times this expression. So we get the natural log of x times z squared times j. And then finally, let's take the partial derivative with respect to z, or let's find fz. And z is inside the natural log function, so we do need to take the derivative of that again. That y will still be on the outside, but it will be multiplied by the derivative of the natural log function here. So once again, we'll have 1 divided by that inside function of x times z squared, but now we're multiplying by the derivative of the inside function with respect to z. So it's not going to be z squared like it was before, because that was with respect to x. Now it's going to be the derivative of xz squared with respect to z. And so x would just be a coefficient of z here. So don't remove that, just take the derivative of z squared. multiply that 2 down, subtract 1 from the exponent, and we get 2x times z to the first power. And don't forget that that is multiplied by k. All right, now let's simplify this gradient vector a little bit before we plug in this point, just to make things a little bit easier on ourselves. And what I notice here is that we have a z squared here and a z squared down here that'll cancel out, so you can cross those out. And then over here, x is in the denominator, x is over here, so we can cross those out. And then this z will cancel out with one of these. So this will become z to the first power, and this z is gone. All right, and so what we have now is y divided by x times I plus the natural log of x times z squared times j plus 2y divided by z times k. And so now we have a much simpler gradient vector that we can work with here. Let's now plug in the point that we've been given to get the specific gradient vector, which will be the specific normal vector at this point on this surface that we can use to find the tangent plane and normal line. All right, so let's plug the point in. We will have the gradient of f of e to 1 is equal to this vector evaluated at this point where x is e, y is 2, and z is 1. So y divided by x is 2 divided by e, that's multiplied by I. Then we have plus the natural log of x, which is e, times z squared. So we have 1 squared, and then that's times j, plus 2y, so 2 times 2, divided by z, which is 1, times k. And now simplifying, there's nothing we can do with the x component, it's just 2 divided by e. But then for the y component, e times 1 squared is just e, and the natural log of e is 1. So we just get plus j, and then plus 2 times 2, which is 4, divided by 1, which is 4, so we get 4k. All right, so that is our normal vector. That is what we will use to find an equation of the tangent plane and a set of symmetric equations for the normal line. So let's work on that now. Starting with the tangent plane, let's set up this equation. A, b, and c will be 2 divided by e, 1, and 4, and then x1, y1, z1 are e, 2, and 1. So we get 2 divided by e times x minus e plus 1, or really you don't even need to write that. You'll just have plus y minus 2 plus c, which is 4, times z minus 1 equals 0. Okay, and then simplifying, you want to distribute 2 divided by e through this quantity and 4 through this quantity. And so when you multiply 2 divided by e by this negative e, the e's will cancel out and you'll just get negative 2. So you get 2 divided by e times x minus 2 plus y minus 2 plus 4z minus 4 equals 0. And then to finish it off, negative 2, and negative 4 become negative 8. Move that to the other side of the equation so that it's positive 8. And the final equation will be 2 divided by e times x plus y plus 4z equals 8. And that right there would be the equation of the tangent plane at this point on this surface. And then let's find the normal line. Using this equation, let's set it up. We'll have x minus e divided by a, which is 2 divided by e. It's kind of ugly, but we can leave it like that. That's fine. That will then be equal to y minus 2 divided by b, which is 1. So I'll just write that as y minus 2. Anything divided by 1 is itself. And then that is equal to z minus 1 divided by 4. And that's it. That would be the symmetric equation for the normal line to this surface at this point. Hey, real quick, before we take a look at the next example, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. For our next example, we want to find the points on the surface at which the tangent plane is horizontal. Okay, so this is an interesting problem. This isn't something that I really talked about in the lesson video for this topic, but it is a problem that we can solve using what we learned about finding tangent planes. Because if a tangent plane is horizontal, what that means is that it's parallel to the xy plane, which means the only difference between a horizontal tangent plane and the xy plane is the value of z that it is located at. In other words, that means that the normal vector would either point in the positive or the negative z direction. There would be no x or y components to that normal vector. The x and y components would be 0. Okay, so what we want to do here is find the gradient vector that would be the normal vector at a point on this surface, and then just set the x and y components equal to 0 and solve for the value of the variables that would make that true. Okay, so let's do that here. Our first step is to get this surface equation in the right form. Specifically, we want all the variable terms on one side of the equation. So let's subtract z from both sides. And so we'll have 0 is equal to 3 minus x squared minus y squared plus 6y minus z. And so that means our multivariable function, f of x, y, z, is equal to 3 minus x squared minus y squared plus 6y minus z. And technically you could get rid of that constant. You could subtract 3 from both sides, but it doesn't matter. When we take partial derivatives to find the components of the gradient vector, the derivative of this 3 will just be 0 every single time, so it doesn't matter either way. All that matters is that we have all of those variable terms on one side of the equation. So now that we have that function, let's find the gradient vector. So we'll take the gradient of f of x, y, z, and that will be equal to the partial derivative with respect to x times I plus the partial derivative with respect to y times j plus the partial derivative with respect to z times k. All right, so starting with fx, you just have to take the derivative of negative x squared. Everything else would be a constant with respect to x. So this is equal to negative 2x to the first power times I plus fy, or the partial with respect to y, and so we only have to worry about these two terms. Everything else is a constant with respect to y. So take the derivative of these two terms, and you get negative 2y plus 6, and that will be multiplied by j. And then technically you really don't need to find the z component because it doesn't play a part in our problem-solving process. But I'll do it anyway because it's fairly quick. The only term we need to worry about is negative z right here. The rest of these terms are constants with respect to z. Their derivatives are 0, and the derivative of negative z is negative 1. So we get minus k. All right, so that's the gradient vector, which would be the normal vector that we would use to find a tangent plane at a point on the surface. But now remember our goal here. We want to find any points where the tangent plane is horizontal, which means that the normal vector will have an x and y component of 0. Okay, so we want to see when that happens. So set both of the x and y components equal to 0. So for the x component, we have negative 2x equals 0. And for the y component, we have negative 2y plus 6 equals 0. Okay, and so now we want to solve for x and y, which should be pretty simple to do here. For the first equation, the only way this is true is if x is equal to 0. You could divide both sides by negative 2 and get that result. But from this equation, we know that x has to be equal to 0. And then for this equation, there's a little bit more work involved. You want to subtract 6 from both sides, and you'll get negative 2y equals negative 6. Divide both sides by negative 2, and you get y is equal to positive 3. Okay, so that's going to correspond to just one point. That's it. There's not going to be more than one point on this surface that has a horizontal tangent plane. The only time it's going to happen is for this x-coordinate and this y-coordinate at the same time. Because when x is 0 and y is 3, the x and y components of the normal vector are 0. Okay, so now we just have to figure out what the corresponding z-coordinate is for that point. And to figure that out, we just have to plug in what x is equal to and what y is equal to into the original surface equation, because that'll tell us the value of z for those x and y coordinates. All right, so what we'll get here is z is equal to 3 minus x squared, which is 0 squared, minus y squared. So we have 3 squared plus 6 times y, so 6 times 3. And so simplifying, we get 3 minus 9 plus 18. And 3 minus 9 is negative 6, plus 18 gives you positive 12. All right, and so that would be the z-coordinate, which means altogether, the only point on this surface where the tangent plane is horizontal is the point 0, 3, 12. That is the answer to this example. Let's take a look at another like this one. Next up, we want to find the points on this surface at which the tangent plane is horizontal. So the same exact type of problem we just did, except now we're working with a different surface. This time we have z is equal to x squared minus x times y plus y squared minus 2x minus 2y. Okay, so we want to do the same thing here. We want to start by finding our gradient vector, which would be the normal vector at any point on this surface, specifically the gradient vector of the multivariable function that we get when all of the variable terms are on one side of the equation. Okay, so in this case, you would just want to subtract z from both sides, and that will give you that function. Right, so in this case, f of x, y, z would be equal to x squared minus xy plus y squared minus 2x minus 2y minus z. All right, and now let's find the gradient vector of that function. The gradient of f of x, y, z will be equal to fx times I plus fy times j plus fz times k. All right, so starting with fx, there are more terms with x in it this time around, so you have to be careful here. Let's go one term at a time. The first one here, the derivative of that is 2x, so we get 2x, and then the second term here, y would be a constant, and so the derivative of x to the first power would be its coefficient of negative 1 times y, which gives us minus y. And then for the next term, y squared is a constant with respect to x, its derivative is 0, and then negative 2x, the derivative of that would be negative 2, and then that's going to be it for fx, because these last two terms are not in terms of x, they are constants whose derivatives are 0. All right, so that's all multiplied by I. Then for fy, let's go one term at a time here. X squared is a constant with respect to y. Its derivative is 0. Then for this term, y is to the first power, so its derivative would be its coefficient of negative x. So we have negative x, and then the derivative of y squared is 2y, so we have plus 2y, and then negative 2x would be a constant with respect to y. Its derivative is 0, and then negative 2y, the derivative is negative 2. All right, so that's all multiplied by j. Again, don't worry about negative z, because with respect to y, it is a constant whose derivative is 0. But then for the last term, again, we don't really need to do this, because you're not going to use this component of the gradient vector to solve this problem. But just for the sake of completion of finding the gradient vector here, just take the derivative of negative z. All of those other terms don't have z in them, so they are constants whose derivatives are 0 with respect to z, and then the derivative of negative z is negative 1. So really we don't have plus, but rather minus k. Okay, so now, remember, a tangent plane will be horizontal when the normal vector has x and y components of 0. So we want to know, when are both of these two components 0 at the same time? So we want to set both of them equal to 0 and then solve this system of equations. So if we set that up, using the x component, we'll have 2x minus y minus 2 equals 0. And then for the y component, we have negative x plus 2y minus 2 equals 0. Okay, now just like I said, we have a system of equations that we need to solve. And so let's work on that next. You could go about this a couple different ways, depending on what different methods you remember from algebra for solving systems of equations. The way I'm going to choose to do it is to solve for one of the variables in one of the equations and then plug it into the other to solve for one variable, and then we will be able to solve for the other. Okay, what I mean by that is in this equation right here, we can very easily solve for x by just adding x to both sides. That will give you this. X is equal to 2y minus 2. And so then you can plug in 2y minus 2 in for x in this equation, and then it's all in terms of y, so you can solve for y. Okay, so that's what I'm going to do here. I'm going to plug in x into this equation. To get this, we'll have 2 times 2y minus 2 minus y minus 2 equals 0. And then simplifying, we have 4y minus 4 minus y minus 2 equals 0. Then 4y minus y becomes 3y, and then negative 4 minus 2 is negative 6, so we have 3y minus 6 equals 0. Add 6 to both sides, and you have 3y equals 6, and then solving for y by dividing both sides by 3 gives you that y equals 2. Okay, so that's our value of y for when both of these two components will be 0, but now we need to find x, which we already sort of solved for. We have x equals 2y minus 2, so now that we know what y is, we can just plug that in and solve for x. So let's do that here. We'll have x is equal to 2 times y, which is 2, minus 2. So we get x is equal to 4 minus 2, which results in x equals 2. So both x and y have to be equal to 2 at the same time for the x and y components to both be 0 for that normal vector. And so we're almost done. We just have to figure out what the corresponding z coordinate is for the point where the x and y coordinates are 2 and 2. So let's plug in these values of x and y back into the original surface equation, and that will give us the value of z on that surface that corresponds to those coordinates of x and y. Okay, so we will get z is equal to x squared, so 2 squared, minus x times y, so 2 times 2, plus y squared, which is 2 squared, minus 2 times x, which is 2, minus 2 times y, which is 2. So a lot of 2's here, giving us that z is equal to 4 minus 4 plus 4 minus 4 minus 4. Okay, so this 4 and this negative 4 cancel out, this 4 and this negative 4 cancel out, just leaving you with z is equal to negative 4. So altogether, the only point on this surface where the tangent plane is horizontal is the point 2, 2, negative 4. That is the answer to this problem. Okay, let's take a look at a different example. Here we want to find the angle of inclination of the tangent plane to the surface at the given point. And our surface is 2xy minus z cubed equals 0, and the point is 2, 2, 2. Okay, so to find the angle of inclination of a tangent plane to a surface, you have to remember what that means, and it's just referring to the angle between a tangent plane and the xy plane. And in the lesson video for this topic, we developed a formula to help us find this. It's based on the formula from earlier in Calculus 3 when we learned how to find the angle between two planes that intersect, which ultimately was just based on the angle between those two planes' normal vectors. So we used the formula for the angle between two vectors. And so by using that formula, within the context of working with a tangent plane, we got the following formula. Cosine of the angle, where that angle is the angle of inclination, the angle between the tangent plane and the xy plane, is equal to the absolute value of the dot product between the gradient vector, del f of xyz, and the unit vector k. And that's divided by the magnitude of that gradient vector. Okay, the gradient vector represents the normal vector of the tangent plane, and vector k represents the normal vector of the xy plane. Okay, so to solve this problem, we need this gradient vector, so let's work on finding that. Our surface equation is already in the right form to find it. All the variable terms are on one side of the equation. So in this case, we would view f of x, y, z as being equal to 2xy minus z cubed. And so then from that, we can find the gradient vector. The gradient of f of x, y, z would be equal to fx times I plus fy times j plus fz times k. All right, so let's find each of these partial derivatives, starting with fx. The partial derivative with respect to x of this function, if we go term by term, this first term will just give us 2y because x is to the first power, so its derivative would be its coefficient, which would be 2 times y. So this is equal to 2y times I, right? That's it, because negative z cubed is a constant with respect to x, so its derivative is 0. Then for fy, the partial derivative with respect to y, it's a very similar derivative. In this case, x is the constant, and y is the variable that we take the derivative of, and y is to the first power, so its derivative is just its coefficient of 2x. And so that's all we'll get, because negative z cubed is not in terms of y, so it's a constant whose derivative is 0. So we get plus 2x times j, and then plus fz, and so we'll take a partial derivative with respect to z. 2xy would be a constant with respect to z, its derivative would be 0, and then the derivative of negative z cubed is negative 3z squared. So we'll write in minus 3z squared times k. Okay, and then we do want to evaluate this gradient at this specific point before putting it into this formula, because we do want to find this angle given that the tangent plane is at this point on the surface. So we do have to take this point into account. So let's plug it in. We'll have the gradient of f of 2, 2, 2, which will give you 4, since y is 2. 2 times 2 is 4. So 4i plus 2x, where x is 2, so we get 4j, and then minus 3 times z squared. Z is 2, so 2 squared is 4, times 3 gives you 12. So we have 12k, or minus 12k. And so now we can set up this formula. We're going to have cosine of the angle of inclination, theta, is equal to the absolute value of the dot product between the gradient vector, or f of 2, 2, 2, with the unit vector, k, and then that will be divided by the magnitude of that gradient vector, f of 2, 2, 2. Okay, and so let's work on that. Cosine theta will be equal to the absolute value of the dot product between this gradient vector and vector k. And remember, vector k is equal to 0i plus 0j plus 1k, right? That's what it is by definition. So if we're taking the dot product of this vector with the gradient vector, the first two terms of that dot product will just be 0, because the dot product is the sum of the product of corresponding components. So if you multiply the x components, you get 4 times 0, which is 0. If you multiply the y components, you get 4 times 0, which is 0. And so really, we're just interested in the product of the z components, which is negative 12 and 1. So negative 12 times 1 gives you negative 12. We will take the absolute value of that. And then in the denominator, we'll have this square root of the sum of the components of this gradient vector squared. That will be the magnitude of that vector. So we have 4 squared plus 4 squared plus negative 12 squared. Okay, so we get cosine theta is equal to positive 12 divided by the square root of 16 plus 144, which altogether will give you the square root of 176. All right, and so then to solve for the angle of theta, you want to use the inverse cosine function, or arc cosine, on both sides of the equation, which will isolate theta, giving you that theta is equal to arc cosine of 12 divided by the square root of 176. And I would recommend putting that into a calculator. If you get it in terms of radians, it'll be a very strange decimal value that's a little bit hard to interpret, so I recommend that you get the answer in terms of degrees, and if you do, you will find that the angle of theta is equal to about 25.24 degrees. Okay, and that's not an exact value. I did round that off to 2 decimal places, but that would be the angle of inclination for the tangent plane to this surface at this point. Or in other words, it's the angle between that tangent plane and the xy plane. Okay, let's take a look at one more example for this video. Alright, so for our last example, we want to find a set of symmetric equations for the tangent line to the curve of intersection of the surfaces at the given point. And we're given two surfaces, x squared plus z squared equals 25, and y squared plus z squared equals 25, and the point is 3, 3, 4. Okay, so this example is unlike anything we have done previously in this examples video, as well as the lesson video, but it's still based on the same ideas that we have been working with in these different problems. And so let's break it down and see if we can understand what's going on here and how we can apply what we know to this problem in order to solve it. And our goal in this problem is to find these symmetric equations for a tangent line to a curve of intersection of the surfaces at the given point. All right, so what that means is that these two surfaces that we've been given, if we were to graph them in the same 3D coordinate system, they would intersect with one another, and that intersection would create a curve. And on that curve will be this point. Okay, so this point would be on that curve of intersection, but it would also be contained by both of these surfaces. Okay, so this point would be on both of them, which means that on both of these surfaces, we could find a tangent plane at that point. Okay, now we're not going to do that necessarily here, but the reason I point that out is because the tangent line to the curve of intersection for those surfaces would have to be contained within that tangent plane. Okay, and so if you want to get a better visual of that, you could try to sketch these two surfaces in a 3D coordinate system, but that's ultimately going to be unnecessary here. Just think of it like this. If this point is on both of these surfaces, and you can find a tangent plane for both of these surfaces at that point, then the tangent line to the curve of intersection at that point would have to be a tangent line contained by both of those tangent planes. And so keep that in mind. I'm going to bring that up again in just a second, because this tangent line would have to be created using a tangent vector, a vector that is tangent to the curve of intersection between these two surfaces at this point. All right, and so our goal is to find that tangent vector so that we can create these symmetric equations for the tangent line, but we currently don't know how we're going to find that. But what's going to help us find it will be the gradient vectors for our surfaces, specifically the gradient vectors of the level surfaces. Okay, so just like we've done in previous examples, we want to view these two functions as multivariable functions of three independent variables, which represent four-dimensional shapes, of which then these two surfaces are level surfaces of. Okay, and both of these equations are in the right form. We have all the variable terms on one side of the equation, and they're equal to a constant. So let's introduce some function notation here. I'll let the first one be f. We'll have f of x, y, z is equal to x squared plus z squared. And then for the second function, I'll let it be g. We'll have g of x, y, z is equal to y squared plus z squared. Okay, so in each case, these represent four-dimensional shapes where these surfaces would be level surfaces of that shape. Okay, and so the gradient vector for each of these two functions would represent the normal vector at any point on these surfaces. And so we do want to find those, but how are they going to be helpful? What would the gradient of f and the gradient of g allow us to do? Well, remember that the gradient vectors would represent normal vectors at a point on a surface, and so you could find the normal vector for each of these two surfaces at this point, and a normal vector at a point would be perpendicular to a tangent vector at that point, right? For a very basic demonstration, if we were to look at this in two dimensions, if you had a curve, and on that curve you looked at a point, and then drew the tangent vector, let's say that this is the tangent vector, the normal vector would look like this, and it would be perpendicular to that tangent vector. Okay, so going back to what I said earlier, at this point on these two surfaces, we could have a tangent plane for each surface. And those two tangent planes would contain the tangent vector for the tangent line, meaning that the normal vector for those tangent planes, which would be the gradient vector, would be perpendicular to the tangent vector. Okay, if there's a tangent vector at a point, then the normal vector at that point will be perpendicular to it. That will happen for both of the tangent planes for each of these surfaces at this point. There is some tangent vector at that point that would be perpendicular to both of the gradient vectors for these two functions. Okay, so why do I bring that up? Well, what we've just determined is that the tangent vector that we're looking for is perpendicular to the gradient of f, and that tangent vector is perpendicular to the gradient of g. That has to be true given this scenario. And so since the tangent vector is perpendicular to both of these gradient vectors, we can find that tangent vector by taking the cross product of these two gradient vectors. Because remember, when you take the cross product of two vectors, what it gives you is a vector that is perpendicular to both of the vectors that you used in that cross product. Okay, so if we take the cross product of these normal vectors from the tangent planes at this point, what we'll get is the tangent vector at that point, which we could then use to create the tangent line to the curve of intersection of the surfaces at that point. So that's what we're going to do here. Let's start by finding the two gradient vectors, starting with the gradient of f of x, y, z. The x component will be the partial with respect to x, and so there's only one x term here. The derivative of x squared is 2x, so we have 2x times I, and then the y component would be the partial with respect to y, but there are no y terms here, so the partial derivative with respect to y would just be 0. So we don't even really need the j term. Let's just move on to the k term, which is where we have the partial derivative with respect to z, and there's only one z term. Its derivative would be 2z. So we have plus 2z times k. All right, then let's find the gradient of g of x, y, z. That will be equal to the x component, which will be the partial derivative with respect to x, but there are no x terms, so that derivative would be 0. So there is no I term. Let's go on to the j term, where we take a partial derivative with respect to y. There's only one y term. Its derivative would be 2y. So we have 2y times j plus, and we don't need this anymore. I'm going to erase it so we have enough space here. But then we have plus the k term, which involves the partial derivative with respect to z. And so we have one z term of z squared. Its derivative is 2z. So we have 2z times k. Okay, so now we have the general gradient vectors, but we do want these specific gradient vectors at this point. So now let's plug in these coordinates into each of them. So we'll have the gradient of f of 3, 3, 4, and that will be equal to 2 times 3, which is 6, times I, plus 2 times 4, which is 8. So we have 8k. That would be the gradient of f at that point. And then the gradient of g at 3, 3, 4, you will get 2 times 3, which is 6, times j, plus 2 times 4, which is 8, times k. And so now we have both of these specific gradient vectors at this point on each of these surfaces. Now we just need to take the cross product of them, and the resulting vector will be the tangent vector at this point for the curve of intersection between these two surfaces. And then we can use that vector to help us create the symmetric equation for the tangent line. All right, so let's set up the cross product. We want to take the gradient of f at that point cross the gradient of g at that point, and that will be equal to this calculation. We want to set up a 3 by 3 matrix and then calculate its determinant. We have I, j, and k for the top row, and then the middle row will have the components of the gradient of f, so 6, 0, and then 8, because there is no j term, so it would be 0. So we have 6, 0, 8, and then the bottom row will be the components of the gradient of g at that point. So that would be 0, 6, and 8. 0 for the x component because there is no I term. So we have 0, 6, and 8. Okay, and then let's calculate the cross product here. We'll start with the I term. So cross out the I column and calculate a 2 by 2 determinant. 0 times 8 is 0, minus 8 times 6, which is 48. So we get negative 48i minus the j term. So we'll cover up the j column, take 6 times 8, which is 48, minus 8 times 0, which is 0. So you just get 48 times j, but it is negative because you make the j term negative. And then finally, for the k term, you want to cover up the k column, and then 6 times 6 is 36, minus 0 times 0 is 0. And so 36 minus 0 gives you plus 36k. All right, so that is the resulting vector. I am going to pull out a common factor here just to make that vector easier to work with. Negative 48, and positive 36 have a common factor of negative 12 that we could pull out. So this would be negative 12 times positive 4i plus 4j minus 3k. And that will just be an easier vector to work with. But what this is here is the tangent vector at this point on the curve of intersection between these two surfaces. And so we're almost done. Now we just have to use the components of this normal vector, which we have simplified by pulling out a common factor. That is fine. We are allowed to do that. And we can construct the symmetric equation of the tangent line. Okay, so remember the form. It's x minus the x coordinate of the point, which is 3, divided by the x component of the vector that you're using. In this case, we're using this vector. So the x component is 4. So we have 4, and then that will be equal to y minus the y coordinate of 3 divided by the y component of the vector, which is 4. And then that will be equal to z minus the z coordinate of the point, which is 4, divided by the z component of the vector, which is negative 3. So that goes down there, and that's it. This right here is our final answer. That is the symmetric equation for the tangent line to the curve of intersection for these surfaces at this point. Okay, so definitely a tricky problem to wrap your head around at first, but once you understand that the gradient vectors for these two functions or these level surfaces would both be perpendicular to the tangent vector at that point, then it makes sense that you could find that tangent vector by taking the cross product of those two gradient vectors. But that is it for this video. This was the last example, but if you do want to get some more practice with this, I have another example available on my membership site. So if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.